Hey everyone, this is Patrick Kennedy with Microchip. In this video, we are going to cover how to implement infrared or IR communications in microcontrollers. To highlight this, we are going to utilize a push button on one device to wirelessly control the brightness of an LED on another device. This example is based on the online MPLab Express tutorial linked in the description. The Express tutorial includes the source code and is based on a larger application note that uses touch control rather than a simple push button and motor control rather than a simple LED, so feel free to check that out once you have this down. Unlike the original example that uses the two Curiosity high pin count development boards with the PIC18F47Q10, I'm going to use two PIC18F47Q10 Curiosity Nanos to accomplish the same goal. I will also be using two Curiosity Nano baseboard for clicks, two Microelectronica IR clicks, and a couple of jumper cables. Speaking of which, let's briefly review how infrared communications, or simply IR comms, works before we get started. Infrared communication protocols are a common wireless communications technology that involves sending serial streams of data through the manipulation of non-visible infrared light. It's still used in a variety of situations, particularly in real-time control applications, since it's low power, easy to set up, and extremely cost-effective. Typical applications include things like television remotes and cordless microphones. IR communication systems generally comprise a transceiver and a receiver. The transceiver consists of a microcontroller as well as some sort of input to specify commands, in our case, a push button, as well as an infrared LED that will transmit the message. The microcontroller processes the command and generates a waveform that drives the infrared LED on and off that are then detected by a light sensor attached to the receiver that allows the microcontroller to decode the signal to determine what command was sent and then fulfill that command. In this case, we are going to use the NEC IR protocol that specifies a carrier frequency of 38 kHz. A typical IR frame comprises marks and spaces that represent logical ones and zeros, and the duration of the mark and space is where information is encoded. The NEC IR transmission protocol depicted here shows how addresses and commands are initiated through a start sequence and culminate in an end sequence. On the transmitter end, we configure the push button as an input to a timer peripheral configured in monostable mode to simultaneously handle the switch bounce as well as generate a pulse identifying which button was pressed. We then decode the input to map to a command stored in a lookup table, which we then use to construct the 32-bit NEC IR frame. To generate the IR frame, a timer peripheral is configured to overflow every 562.5 microseconds defined by the NEC standard. The timer overflow is fed into two separate blocks of logic gates comprising configurable logic cell or CLC peripherals that each output logic 1 and 0 that form the building blocks of the IR frame we saw earlier. The logical 1s and 0s, or marks and spaces if you recall, are then multiplexed to produce the mark and space NEC IR frame. A PWM and timer peripheral are simultaneously used to generate the 38 kHz carrier frequency, which is combined with the CLC generated IR frame and the digital signal modulator or DSM peripheral to produce the modulated frame which is transmitted by the LED. For the receiver, we use a hardware limit timer peripheral to monitor the port pin that will alert us when a valid falling edge is detected. A capture compare or CCP peripheral combined with another timer are configured to detect start and end sequences as well as logic 1 and 0, which are then decoded to determine the sent command. This is followed by a corresponding control action, which in our case is simply varying a PWM duty cycle. Let's get the transmitter up and working. Here I have the Express project open in MPLabX. We are going to open up MCC and look at the pins to see if any changes need to be made. I'm going to focus on using one push button to control one LED as I only have one of each on the Curiosity Nano boards. From the schematic, we can see that the push button is tied to pin RE2, which is only usable as a general purpose I/O pin. I want it to serve as an input to one of the timers that are already tied to RC5 and RB4. I'm simply going to tie the Curiosity Nano push button on pin RE2 to RC5 using a jumper cable. This means I'll also need to head over to the pin module and enable a weak pull-up resistor on pin RC5 so we can detect a change in the push button. According to the Express tutorial, the RC5 pin controls the PWM3 output on the receiver microcontroller. I can also see that the DSM module is configured to output the modulated IR frame to pin RD1, which is connected to the PWM micro E bus pin on the Curiosity high pin count. I can see on the Curiosity Nano schematic that this pin does not correspond to the PWM micro E bus for the click baseboard I'm using, so I will change it to RA3, which I see should be adequate for the micro E bus. We then just need to generate our code and build the project. Here we can see that the behavior of the output pin on RA3 from the DSM is exactly what we expect. Let's move on to the receiver. Here I have the Express project open in MPLAB-X. We are going to open up MCC and look at the pin manager to see if any changes need to be made. Looking at the pin manager, I can see that timer 2 is configured to receive an input from port RA1. Opening the timer 2 configuration tab under project resources, I can see that timer 2 is in fact configured to detect a start sequence, which I can confirm by checking out the Curiosity high pin count schematic. Looking at the PIC18F47Q10 Curiosity Nano schematic, I can see that port RA1 is tied to the click module number 2 on the baseboard. So this code will still be valid if I place my IR click on that spot. The outputted PWM signal is on RA4, which also corresponds to click module number 2. So I'll need to reroute to a different pin like RA3 to avoid any potential interference issues with the click. Next, I need to make sure that the PWM3 module that we learned earlier is the one we are controlling is correctly routed to the LED on the Curiosity Nano. According to the schematic, the LED resides on pin RE0, which is only configurable as a general purpose I/O. To get around this, I'm just going to use a jumper cable to tie pin RA3 where my PWM3 module is set as an output to RE0 where the LED resides. Once this is done, we can go ahead and hit generate code and then build the project. Looking at the hardware, we can see that the behavior of the system is as expected with the push button sending data over IR to vary the duty cycle of the PWM up and down. Check out the link in the description for the source code, step-by-step walkthrough, and other links for hardware used in this video. Thanks.